This is the Edexcel IGCSE January 2022 physics paper, suitable for both double and triple award. Question 1. The region of space around a magnet is known as a magnetic field. Which of these diagrams correctly represents the magnetic field around a bar magnet? Now, just so you guys know, a bar magnet looks like this. You guys might have used it at school or seen it somewhere. It looks like a bar. The thing about magnetic field is that you need to appreciate that it's a vector. And vectors have both, as you remember, magnitude and direction. Now, the direction is important here because the direction of magnets, of magnetic field, is always from north to south, And once you know that, you should be able to answer the question. So which one is correct? North to south. That would be B. It's going from north to south. See that? Okay. Part B, the diagram shows two bar magnets placed close together. Which of these describes what happens to the two magnets? Again, magnetic field goes from north to south. Therefore, opposites attract. Opposite means either north and south or south and north. Opposites attract, therefore they attract. Just so you guys think a little further, what if they wrote S and S here, right? So the N is on the other side. If the bar magnets were placed like this, what would happen to them? How would you choose it then? Then you would choose repel, isn't it? Because south and south, like and like repel, then the answer would be repel. Okay. Which of these magnet arrangements gives a uniform field between the poles? Okay, uniform field. This is important because sometimes they tell you to draw it. Uniform field means the strength of the magnetic field is uniform. Uniform means the same everywhere, like school uniform means everyone wears the same. So a uniform field is where the magnetic field is the same everywhere. That only happens when the magnets are lined up neatly, either like C or like B. Right? Because if they're like that, then the field would be more curly, and that wouldn't be uniform. That would not be the same everywhere. So is it C or B then? Which one has a uniform magnetic field? You go back to your basic knowledge about magnets. Magnets are attraction between opposites. Which one has attraction north and south, right? Because they're opposites. Would this one have any attraction? No way, because north and north actually repel. So they would not even have a magnetic field between them because they're too busy repelling each other. Therefore, the answer is C. And just so you guys know, sometimes they ask you to draw the uniform magnetic field. And if they told you to do that, how would you draw the uniform magnetic field? You would bring a ruler, take out the ruler, and draw at least 3 straight lines going from north to south. And they must be evenly spaced out. So the space here and the space here needs to be the same. And you must have the arrow pointing correctly from north to south. Okay, so if they ask you to draw a uniform magnetic field, that's how you would do it, like the purple lines here. Next question says, state the name of a material that would be suitable for use as a permanent magnet. Permanent magnets are usually hard magnetic material, and the most well-known one would be steel. You can also put down nickel and cobalt. These are some other magnetic materials. Iron is magnetic, but it's not the best one to use as a permanent magnet, because iron is a soft magnetic material, so therefore it's not always permanent. So the best answer is steel. Steel. Permanent magnet, steel. Okay, next, describe an investigation that could be used to determine the shape of the magnetic field around a bar magnet. Okay, whenever you see a question, usually 3 or even more marks on designing an experiment or describing an experiment, an investigation, you have to do it systematically. The way you do it is, imagine you're going to bake a cake, okay? If you're going to bake a cake, you need to have a shopping list. You need to go buy eggs, you have to go buy milk, flour, like if you don't have your ingredients, you cannot make the cake. So it's the same thing for an experiment. When you make an experiment, you must have a list of what we call apparatus. So instead of shopping list, you think of apparatus. Apparatus means the things that you're gonna use, the equipment you're gonna use for your experiment. Once you write out your apparatus list, guys, at least you're getting some marks for yourself, and then you start to organize them into an answer and put them together into like experimental steps. Okay, so now let's think. If I'm going to figure out the magnetic field around a bar magnet, what do I need? What equipment do I need? What's on my shopping list? What do I have to gather in order to do this? Definitely start with a bar magnet, right? So I'm going to have a bar magnet. What else? I'm going to show you the picture of the actual experiment. Okay, so this is how you would actually do this experiment. You would have this bar magnet, which looks like this in real life, right? And the bar magnet has a north and a south. So you put the bar magnet there, and then you put a piece of paper, this piece of paper on top of it. So it covers the bar magnet, which is underneath. Then you're going to get what we call iron filings. Iron filings. Iron, because it's magnetic. Filings just means like powdery bits of iron. Iron filings, you're going to pour it all over. And what it'll actually do is it's going to arrange itself. Look at this. Like this. These little gray bits here you're seeing, that's the iron filings, the iron powder basically. And it'll arrange itself into this pattern. It's not random, right? This beautiful pattern around this bar magnet. So once you have the iron filings, you can already see the shape, right? You can see the shape. But that's not enough, because you don't know the direction, and you need to show the direction because magnetic field lines have direction. How can you figure out the direction? This pattern does not show you which direction they're going in, right? So how do you measure direction? What is the equipment you're going to use? Compass. Compass. Therefore, compass over here, that's the other equipment that you need. So if you just look at this diagram, now you can start to string all this together into an answer, isn't it? You're going to write, you need a bar magnet, okay, and then you're going to need iron filings. What other equipment? You need plotting compass, or just compass, plotting compass. And also, you need to have pen and paper, isn't it? Because you're going to draw these lines and then draw the arrows onto them. So paper and pen. Once you do that, you can start to describe the experiment, which is basically put paper on bar magnet, and then you're going to sprinkle the iron filing. Don't just write metal filings, because not all metals are magnetic, so it's got to be iron filings. Filings is one L, it's not fillings. Sprinkle iron filings, and then and you're going to trace the magnetic field lines with pencil. Magnetic field lines with pencil, so you can see the direct, well, not the direction yet, but at least you see where the field lines are. So you're gonna draw these shape like this, and so on. Then you have to use the plotting compass to see the direction. Use plotting compass for direction. Done. So question 2 says, a scientist wants to determine the half-life of a radioactive isotope, and he measures the count rate from the radioactive isotope. State how the scientist should correct the count rate for background radiation. Okay, now let's just take a look at the actual experimental setup. This is how you do an experiment when you want to investigate the radioactive activity of a material. You have, again, just like the previous question, what is your list of ingredients, what is your shopping list, right? What is your apparatus you're going to use? You need a radioactive source. You need a GM tube, this thing, which measures the radioactivity. And then you need a stopwatch. These are your apparatus. Then you need to understand what's going on. So when you put this radioactive source here, it's going to give off radioactivity. And when it does, it's going to show up as a reading on this GM counter. However, let's say I removed this radioactive source. There's nothing there. Even with nothing there, the counter is going to read a number. It's going to read the background radiation. So even where you are sitting right now, there's background radiation. It's very low, so it doesn't really affect you, but it's there, which means that you need to subtract the background radiation from your actual reading if you're going to measure the reading of your radioactive source. Does that make sense? So let's say without the radioactive source, this thing reads 5. This thing reads 5. Then when you put the radioactive source there and it reads 104, then you have to do 104 minus 5, which is 99, and that is the actual radioactivity of your source. So therefore, the answer is you have to subtract the background radiation or the background radiation reading. Okay, next question. Now here it says, the graph shows how the activity of the radioactive isotope varies with time, and explain what is the meaning of the term half-life. Half-life. Do you guys understand this graph? This graph shows how the activity of this radioactive isotope drops over time, right? And the word half-life is examined a lot, usually 2 marks. So I want you guys to always get these 2 marks. Definition is the amount of time taken for half of the radioactive nuclei to decay. So the key word here is amount of time. That's the life, because life is measured in time. For half of the radioactive nuclei, that's the half to decay. Memorize this definition. And the next question asks for the half-life of this isotope. So what is the half-life of this isotope? As you just said, is the time taken for half of it to decay, right? So at the beginning, at time 0, what is it? The activity is 50. Now you look at when it drops by half. So what's half of 50? Divide by 2, right? So that's 25. So at 25, what is the time it takes to drop down to 25? That would be, this is 3. Therefore, this number should be 2.2, 2.4, 2.6. 2.6 minutes is the answer. Okay, question 3. Here it says, Wi-Fi signals are electromagnetic waves that can be transmitted at frequencies of 2.4 gigahertz and 5.2 gigahertz. Giga is a billion, so it's 2.4 billion hertz. And A says, state a similarity of the Wi-Fi signals at 2.4 and 5.2 gigahertz. If you know anything about electromagnetic waves, you know that they always travel. They're able to travel or can travel in a vacuum. That's just the behavior, one of the characteristic behaviors of electromagnetic waves. The other thing that all electromagnetic waves have in common is same speed. Both have the same speed. So even though 1 hertz is much bigger than the other hertz, they're traveling at the same speed. Part 2, the 2 Wi-Fi signals have different frequencies. State another difference between the Wi-Fi signals. Since they have the same speed and their frequency is different, that means their wavelength is also different. And if you're not convinced, I'm going to show you in the next question. Different wavelengths. So the next question asks for the formula linking speed, frequency, and wavelength. And that would be speed or velocity equals to frequency times wavelength. And now you should be able to see that since speed stays the same, right? Speed stays the same. If it stays the same, that means if my frequency is higher, then my wavelength must be lower. Do you see that? So if frequency changes, then wavelength also changes. In other words, if frequency is different, then wavelength is also different. And they actually have an inverse relationship. So the higher the frequency, the lower the wavelength, and vice versa. Next part, calculate the wavelength of Wi-Fi signals transmitted at 5.2 times 10 to the power of 9 hertz. So let's use that equation basically. The speed is 3 times 10 to the power of 8. So 3 times 10 to the power of 8 is equals to frequency times wavelength. Now, please rearrange to make what the subject. What are you trying to find here? You're trying to find the wavelength. Therefore, wavelength should be the subject. So wavelength is equals to 3 times 10 to the power of 8, which is the speed, divided by frequency. And frequency is this number here, 5.2 times 10 to the power of 9. 5.2 times 10 to the power of 9. And if you do that on your calculator, you should be getting 0.058 meters. So please rearrange. When I look at the mark scheme, one of the steps that you get a mark for is rearranging the equation. Rearrange to make what you're finding the subject. Make wavelength the subject. And part C, which type of wave is a Wi-Fi signal? At the top, it says Wi-Fi is a type of electromagnetic wave. And you should know that all of the electromagnetic waves are transverse waves. Transverse waves. So please remember that. All electromagnetic waves are transverse waves. Okay. And then says here, describe the difference between a transverse wave and a longitudinal wave. You may draw a diagram to help your answer. Right, this diagram is very helpful. This one on the left, this is a transverse wave. And the one on the right is a longitudinal wave. Now, I want you to have a few keywords in mind when you describe this. You need to mention the direction, which is here. See, direction is this way. And then you have to mention the vibration, which for the transverse wave is up and down. Do you guys know what's going on? Just imagine you're this hand, right? And there's this spring. And you're going to hold on to the spring here, and you're going to move it up and down. So you're going to go up and down, up and down, up and down with your hand. And therefore, the spring is going to move up and down and up and down. But as it moves up and down, the spring is actually going to carry the wave across to the other side of the room. Can you imagine that? Therefore, your vibration is vertical, because you're moving your hand up and down, whereas the direction of travel is horizontal. So do you see the green and the pink? What is their relationship? They have a perpendicular relationship, and that is how you define a transverse wave. A transverse wave is when the direction, which is the pink, is perpendicular to the vibration, which is green. All of these are key words. So direction is perpendicular, and I hope you can see the perpendicular just now. On the other hand, look at this diagram. Longitudinal, your hand is still holding the spring here, but this time, instead of moving it up and down, you're going to move it left and right. You're going to move it horizontally. And as you move it horizontally, you can imagine the spring is going to go like doing, 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 doing. So it's still going to carry the wave to the other side of the room horizontally. In other words, you are vibrating the coils horizontally. So the vibration is horizontal. And it's also going to travel horizontally across the room. Now look at the relation between the pink and the green. This is the pink, this is the green, what is this? This is parallel, right? These are two parallel lines. There's no right angle, there's not perpendicular. And therefore, the definition of a longitudinal wave is the direction, green, is parallel to the vibration, the vibration, which is the green, is parallel to the direction, which is the pink. So it's parallel. to the vibration. Does that make sense? So this is how you define transverse and longitudinal waves. And just to take this step a bit further, because sometimes they ask that, an example of a transverse wave is any electromagnetic wave. It could be visible light, ultraviolet, infrared, gamma rays, X-ray. All of these are transverse waves. So any of them, if you want to give an example. And an example of a longitudinal wave is a sound wave. So when you're listening to me right now on your computer, on your phone, that wave is reaching your ear from the speaker to your ear via longitudinal sound waves. So in this video, we talked about the red box, transverse and longitudinal waves. Know the definition and know the examples of each of them. Definition of a transverse wave is that direction is perpendicular to the vibration. An example would be light. Longitudinal waves, the direction is parallel to the vibration. An example will be sound. Light and sound. Blue box, this is a little bit about magnetism. This is a bar magnet. Make sure you know that the magnetic field lines have magnitude and direction, and the direction is always from north to south, hence these arrows over here, north to south. And what is this down here? What is this called? What are the three purple lines representing? It represents a uniform magnetic field. Know how to draw it. 3 parallel lines evenly spaced with the direction as arrows. Green box down here, this is the experiment for finding out the magnetic field lines around a bar magnet. Know your shopping list. You need iron filings, plotting compass, bar magnet, paper, and pencil. And then finally, purple box, know the definition of half-life. It is the amount of time for half of the radioactive nuclei to decay. And how to find the half-life, you find the top half of it, go across and look at what that time is, and that time will be the half-life. That is 1 half-life. And then finally, the experimental setup for investigating radioactivity, including, again, your shopping list, your apparatus, the radioactive source, the GM tube, GM counter, stopwatch. And finally, to subtract the background radiation from your experiment.